Here is a puzzle Newton wrestled with for years. When you weigh an apple, all of the earth pulls on it, the rock beneath your feet, and the rock on the far side of the planet, thousands of miles away. Yet we routinely treat the whole Earth as a single point at its center, and it works. That shortcut needs a proof. The proof is one of the most elegant results in classical mechanics, the shell theorem. We will earn it by summing the pull of every piece of a thin, spherical shell. We start by simplifying the target. A solid sphere is just a nested stack of thin shells, like the layers of an onion. If we can find the force from one uniform shell, we integrate over all the shells and the whole sphere follows. So the real problem is a single shell, mass m sub s, radius r, and a point object of mass m sub 1, sitting a distance r from the center. We will prove two claims. First, when the object is outside the shell, with r greater than r, the shell pulls exactly as if its entire mass sat at the center. The force is minus gm sub sm sub 1 over r squared, pointing inward. Second, when the object is inside with r less than r, the net force is precisely zero. Our strategy is direct. Chop the shell into tiny area elements, find the pull from one element, then add them all up by integration. Set up coordinates. Let the z-axis run from the center of the shell straight to the object. So the object sits at position z along that axis, with z at least 0. Take the first case, the object outside, so z is greater than the radius r. Now describe any point on the shell with spherical coordinates. A polar angle theta measured down from the z-axis called the colatitude, and an azimuthal angle phi swept around the axis. On the surface, the radius equals r, so the point's coordinates are r sin theta cosine phi, r sin theta sin phi, and r cosine theta, with theta running from 0 to pi and phi from 0 to 2 pi. Carve out a small patch between theta and theta plus d theta and phi plus d phi. Its two edges have lengths r d theta and r sine theta d phi, so its area is r squared sine theta d phi. The shell's mass is spread uniformly, with surface density sigma equal to m sub s over 4 pi r squared. So the mass element is dm equals sigma r squared sine theta d phi. Now the key idea that makes this tractable, symmetry. Pick one mass element on the shell. Its gravitational pull on the object has two parts. One component pulling the object along the negative k-hat direction down toward the center line, and one component pulling it sideways away from the z-axis. Here's the trick. For every element, there is a twin directly across the axis at the same colatitude theta, but with phi rotated by half a turn, plus or minus pi. That twin has the same mass and lies the same distance away, so it pulls with the same strength, but its sideways component points the opposite way. Add the pair and the sideways pulls cancel exactly, while the downward pulls reinforce. Every element has such a partner, so across the whole shell, every sideways contribution is cancelled. Only the component along the axis, the z component, survives. That collapses a hard three-dimensional problem into a single integral. So we only need the z component from each element. Draw the triangle, the center, the object at distance z, and the element out on the shell at radius r. Call the length of the line from the element to the object r sub s1. By the law of cosines, r sub s1 squared equals r squared plus z squared minus 2rz cosine theta. The force from the element points along that line and makes an angle alpha with the z-axis. So its z component is minus gm sub 1 dm over r sub s1 squared times cosine alpha. Substitute the mass element dm we just found. The z component becomes minus g m sub s m sub 1 over 4 pi times cosine alpha sine theta d phi I over r sub s1 squared. Now integrate over the whole surface, theta from 0 to pi, phi from 0 to 2 pi. Nothing in the integrand depends on phi, so the integral simply contributes a factor of 2 pi. The 4 pi in the denominator becomes a 2, and the total axial force is minus gm sub s m sub 1 over 2, times the integral over theta of cosine alpha sine theta over r sub L1 squared d theta. The integral looks forbidding because cosine alpha, sin theta, and r sub s1 all change together as theta sweeps. The cure is to change the variable of integration to r sub s1 itself, using the law of cosines twice. First relation from the triangle we already have. R sub s1 squared equals r squared plus z squared minus 2rz cosine theta. Differentiated, holding r and z fixed. 2r sub s1 d r sub s1 equals 2rz sine theta d theta. So sin theta d theta equals r sub s1 over rz times dr sub s1. That disposes of the sin theta d theta piece. Second relation, the law of cosines taken from the object's corner, r squared equals z squared plus r sub s1 squared minus 2r sub s1, then cosine alpha. Solve that for the cosine. Cosine alpha equals 1 over 2 z sub s1 times the quantity z squared minus r squared plus r sub s1 squared. Now every piece of the integrand is written in terms of r sub s1 alone. Assemble the outside case, z greater than r. As theta runs from 0 to pi, the leg r sub s1 grows from z minus r to z plus r. Those become our new limits. Substitute both replacements. The sin theta d theta brings a factor r sub s1 over rz. Cosine alpha brings the bracket over 2zr sub s1. And the 1 over r sub s1 squared is already there. Collect the constants and the powers of r sub s1, and the messy integral flattens into minus gm sub s m sub 1 over 2 times 1 over 2rz squared times the integral from z minus r to z plus r of the quantity z squared minus r squared over r sub s1 squared plus 1 dr sub s1. No integral tables needed. The first term integrates to minus the quantity z squared minus r squared over r sub s1. The second integrates to r sub s1. Evaluate at the limits. At the top limit, the antiderivative gives 2r. At the bottom limit, it gives minus 2r, and the difference is 4r. Multiply the constants. 1/2 times 1 over 2rz squared times 4r. The r cancels, and the 4 over 4 is 1, leaving minus gm sub s m sub 1 over z squared. That is exactly the force of a single point mass m sub s at the center. The first claim is proven. Now the inside case, z less than r with the object buried within the shell. The geometry barely changes. The only thing that moves is the range of the leg r sub s1. When the object sits inside, as theta runs from 0 to pi, the leg runs from r minus z to r plus z. Everything else in the setup is identical, so we reuse the very same antiderivative, minus the quantity z squared minus r squared over r sub s1 plus r sub s1, now evaluated between r minus z and r plus z. At the upper limit, the antiderivative gives 2r. At the lower limit, it also gives 2r. Their difference is 0. So the entire force is minus g m sub s m sub 1 over 2 times 1 over 2rz squared times 0, which is exactly 0. Inside a spherical shell, the pulls from every direction balance perfectly and the gravity vanishes. The second claim is proven. 2 limits, 1 integral, and both claims fall out. Outside the shell, with z greater than r, the force is minus g m sub s m sub 1 over z squared. The shell pulls exactly as though its whole mass were crushed to a point at the center. Inside, with z less than r, the force is precisely 0. Now return to the solid sphere. It is nothing but a nested family of shells, and each one, seen from outside, acts like a point at the shared center. Add them, and the entire sphere pulls as a single point mass at its center, which is the assumption we leaned on all along for the Earth and the Moon. And the second result is just as striking. Hollow out a planet, stand anywhere inside the shell, and you feel no gravity from it at all. That is the shell theorem. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.